Okay, YouTube, this is our first video in which we're going to begin our exploration of what we refer to as the natural base or the number e. And so let's go ahead and start with what the number e is and talk about how we kind of evaluate expressions involving e, and then we'll move forward from there to graph exponential functions involving a base of e. And so starting with this, basically in the history of math, this says here that it's marked by the discovery of special numbers such as pi and say I. And so for instance here we know pi is exactly, I say approximately, I can't write it all, but 3.14159 and so on and so forth. Whereas I of course is the square root of -1. What we're going to do is introduce another special number, and we're going to call this number e. And e because it is referred to as Euler's number. And Leonhard Euler, was the Swiss mathematician who developed kind of the thinking behind this. But he said that the expression 1 plus 1 over x, all of this to the x power, approaches this number as x gets very, very, very big. And so what you can see here essentially is that this number e is developed when we start substituting in values for x here. And you can see that we've graphed this on the right. But if we allow the y-axis to equal what we get when we take 1 plus 1 over x to the x power, as x gets bigger and bigger, as x gets, say, 10, we get the value of this as being 2.593. And we can see that 10 actually occurs on our graph right here, and we say that that height is about 2.593 if you trace it over to about right here. But they say as we plug in bigger and bigger numbers like 10 squared or 100 or 1,000 or 10,000 or 100,000 or a million, what you start to see is that the value of this overall expression gets closer and closer and closer to this value of about 2.71828. So that is to say that if we were to go out to the right on this graph here, as this x value gets larger and larger, what we're really approaching is this value of e. And we're going to say that the natural base e is an irrational number. That's just to say that when it's irrational, it does not terminate. So it doesn't terminate. Okay. And it doesn't repeat. Okay, it doesn't repeat. It's not going to be 0.33333 or something like that, or 0.123, 0.123, 123, 123, 123, but it doesn't repeat. And so we have this irrational number, and we say that it's defined as follows. We say that as x gets very, very large, the value of this overall expression, which you don't have to know this expression, but you do need to know this, approaches approximately this value right here. And so with, I guess for all intents and purposes, what we'll say is when it comes to knowing e, we typically know e is 2.718. And so one thing that I want to know right now is this. E is a number, so e is the natural base. We call it the natural base. And we say e is a constant. It is a number, okay? And so it's never going to change. It's always equal to this 2.718-ish. And if you want to go beyond that, then I suppose we could extend this here. And so what we're going to see is basically a lot of the time we call this the natural base because, as you notice with these expressions over here, we have e as the base of some exponents, and we often have e as a base on exponents. So one thing that we can expect to do from time to time is evaluate or simplify expressions containing a base of e. And what I want you to know is that it follows the same rules that we've followed before for rules of exponents. So if we said a to the m times a to the n, remember that when we multiply two things with the same bases, we would add their exponents. Likewise, if we were to divide two things with the same bases, we would subtract their exponents. And we know that if we have a power, so like a to the m, if we raise that to the n, we would get this a to the m times n up here in our exponent. But essentially, these were our rules of exponents in the previous chapters. We say that going forward, we see that something like e to the third times e to the sixth, because they both have a base of e here, we're going to say we do get e, but we get e to the 3 plus 6. So in other words, we really just get e to the 9. Now I'm going to put a box around this, and we're going to label this. This is the exact value of this expression right here. What I want to be able to do is also develop an approximate value. Now, it is not so important to me that you find an approximate value on this set of problems. But what I do want to show you is that on a calculator, we do have an E button. It's just that you're going to notice that the E button, and it's kind of small here. Let me try to bring it up over here. Behind the button that says LN, there's this little icon, and it's in yellow on my calculator, but it says e to the x power. And I want you to see what happens when I type this in here. If I hit second LN, or yellow button LN, what happens is it pulls up e to the blank. Now, the interesting thing about this is because e is the natural base, then it's always usually the base of an exponent typically. So what we're going to see is that it's always asking, what are you taking e to the power of? And in this particular case, we're taking e to the 9. So what I want you to see is we get about 8103.1. So we get approximately 8103.1. And we can get a decimal on this, but we would say it exactly equals e to the ninth. So looking at letter B here, we have a quotient. We would just treat this as we normally would. Starting with our coefficients here, we say 16 divided by 4. We would end up with 4. Now e to the fifth over e to the fourth would be e to the 5 minus 4 power. So really what we end up with here is 4e to the first, or just 4e. And so to get this on a calculator, how would I do this on a calculator? We would say that we would take 4 times, now, e to the power of, and we're just going to have to say, well, if it's just e, then I suppose we'll raise it to the power of 1. But 4 times 2.718 would be approximately 10.9. So it's approximately 10.9. So for this last expression, we see here, we actually have a property of exponents that says if you take, say, a product to a power here, then we have to raise every factor in that product to this power. So as long as this is a product right here, then we can kind of distribute this power throughout. And so we get this power to a power rule, but for each of our individual terms. So for instance here, we would say, well, all of this to the second, because we have a product in here, we get 3 to the 1 times 2, or 3 to the 2, times now e to the negative 4x times 2, which is negative 8x here. And so something we're going to see happen from time to time is that we basically can simplify these expressions. So for instance here, I know that this is a 9e to the negative 8x. And the other thing I want to mention about this is if we have a negative exponent, okay? Let's remember a rule for negative exponents. We say that anything to the negative m would be the same thing as the reciprocal of that thing to the positive m, or we could move it down across this fraction bar here. So we'd say that because this has a negative exponent, we could put all this over 1. What we'll do is we'll just leave the 9 up top and move the e downstairs. What we get is e to the positive 8x here. So this would be our simplified expression. So e is a number. It is 2.718-ish, and we will deal with it as being our base often. Cheers.